A vast ocean stretches in every direction, not of water but of space itself, an endless cosmic sea, black and silent, speckled with islands of fire. Galaxies glow like embers scattered across an eternal night, drifting apart as if carried by invisible tides. But hidden in this quiet sea is something beyond imagination. A force so profound it reshapes reality itself. It bends the geometry of space, slows the passage of time, and decides the fate of everything that has ever existed. This is not a star, burning with thermonuclear fury. It is not a supernova, detonating with the brilliance of a billion suns. It is not even a black hole, with its gravity so strong that not even light can escape. This power is quieter, stranger, and infinitely more vast. It is not merely destructive. It is the engine that drives the cosmos forward, pushing every galaxy farther from every other, rewriting the destiny of the universe moment by moment. What is the most powerful thing in existence? Is it a force of nature? A weapon beyond comprehension? Or something so fundamental that reality itself could not exist without it? Tonight, the journey begins. A descent into the deepest mystery science has ever faced. A search for the hidden hand that holds the universe, for the power that has shaped the past, is reshaping the present, and will decide the far future of everything. This is not just a question about the cosmos. It is a question about existence itself. If you are new here, join the journey. Like, subscribe, and let's begin. For most of human history, the heavens appeared eternal and unmoving, a perfect dome of light suspended over a still earth. The stars did not seem to change. The planets traced slow, patient paths across the sky. Power, in those early nights, was seen as divine, beyond reach, the work of gods and spirits. Then came a quiet revolution. In the late 17th century, a man sitting beneath an apple tree imagined the unseen threads that hold the world together. Isaac Newton gave these threads a name, gravity, and in that naming, the universe was no longer the domain of gods, but of laws. He saw that the same mysterious pull that brought an apple to the ground was the force that kept the moon tethered to the earth circling the sun, and the planets locked in their silent dance. Gravity, invisible yet absolute, became the first candidate for the most powerful thing in existence. For centuries, it ruled unchallenged. Scientists imagined a universe like a great celestial machine, running on clockwork precision, its gears turned by the constant pull of Newton's force. But power has a way of hiding its deeper layers, and the early 20th century revealed that the picture was not yet complete. In 1915, Albert Einstein redefined gravity itself, no longer a force, but a bending of space-time, a cosmic stage warped by the presence of mass and energy. Where Newton saw an invisible string, Einstein saw the fabric of the universe flexing and curving, cradling planets in invisible wells. With general relativity, gravity became something deeper, more elegant, a whisper written into the geometry of reality. For decades, scientists believed this warping of space-time would one day slow the universe's expansion. The Big Bang had thrown galaxies outward, but gravity was expected to hold them back, pulling against the momentum, dragging the cosmos into a gradual deceleration. Some imagined that gravity might even succeed completely, halting expansion, reversing it, and drawing all matter back into a final cataclysm, a big crunch. Then came the night sky's quiet betrayal. In the 1990s, 2 international teams set out to measure the rate of this cosmic slowdown. They chose as their guide a special kind of star death, type Ia supernovae, stellar explosions so perfectly bright they could be used as cosmic mile markers. By comparing their apparent brightness with their redshift, the stretching of light due to cosmic expansion, astronomers could map how the universe's speed had changed over billions of years. Saul Perlmutter's supernova cosmology project scanned the heavens with relentless precision, while Schmidt and Adam Riess led the High-Z supernova search team across mountaintop observatories in Chile and Australia. These scientists expected to see the universe's expansion curve bending downward under gravity's grip. But when the data came in, it did not bend downward at all. It curved upward. Instead of slowing, the universe was accelerating, rushing outward faster and faster as time went on. The discovery landed like a thunderclap. Something was not merely resisting gravity, but overwhelming it on the largest possible scale. The invisible hand that Newton had uncovered was being pushed back by an even more mysterious one, a kind of anti-gravity written into the very vacuum of space. It was the most shocking discovery. In modern cosmology, the results were checked, rechecked, and checked again. More supernovae were observed, more data compiled. The curve did not change. The acceleration was real. The universe was not coasting toward rest. It was running and picking up speed. This was the birth of a new cosmic entity, dark energy. No one could see it, measure it directly, or bottle it in a lab, but its fingerprints were everywhere. In the glow of distant supernovae, in the faint afterimage of the Big Bang known as the cosmic microwave background, in the vast scaffolding of galaxy clusters stretching across the night, roughly 70% of all that exists appeared to be this invisible pressure, quietly driving galaxies apart. Overnight, our understanding of cosmic power shifted. Gravity, once crowned as the ruler of the universe, had been dethroned. Something even stronger, more pervasive, and more enigmatic was now in charge. A force that did not pull, but pushed, inflating the very fabric of reality. This was the moment humanity first glimpsed the true scale of power hidden in the cosmos. The sky above was no longer a static dome, nor a slowing explosion, but a living, breathing thing, a universe caught in a great escape, driven by a presence we could not name. And in that revelation came a new kind of fear. For if this unknown energy could accelerate the universe today, what might it do tomorrow? The discovery did not make sense. For centuries, gravity had been the master architect of the cosmos, the invisible sculptor shaping the orbits of moons, the fall of rain, the collisions of galaxies. It was the force that stitched reality together, the quiet power that turned chaos into order. To find that this ancient ruler was losing its grip felt almost heretical. The data was unrelenting. Supernova after supernova told the same story. The universe was not slowing, it was running. And with every billion years that passed, its pace quickened. Imagine an explosion. The first instinct is to think of its fireball gradually fading, its debris scattering more and more slowly until it finally stops. That was how astronomers expected the universe to behave. The Big Bang was thought to be a single great flash of creation whose force would eventually wane, but the cosmos was doing the opposite. Its expansion was not fading, it was accelerating, as though some unseen hand was leaning harder and harder on the cosmic accelerator. This was more than surprising. It was unsettling. It meant there was something else at work, something vast, invisible, and powerful enough to fight gravity across the whole of existence. Something that pushed galaxies apart even as their gravity tried to hold them together. This revelation shattered the hierarchy of cosmic forces. Gravity, which had once seemed unchallenged, was now revealed to be merely one actor in a larger, stranger drama. The universe was not just drifting, it was being driven, and what was driving it defied every expectation. Astronomers called it dark energy, not because they understood it, but because they did not. It was a placeholder, a name for ignorance, yet this ignorance accounted for nearly 70% of everything that exists. That number alone was enough to leave physicists silent. Imagine a puzzle where most of the pieces are invisible. That was the new picture of the cosmos. What made this discovery even more disturbing was the strength of this hidden power. It was not simply balancing gravity, it was overwhelming it. All the matter in the universe, every star, every planet, every atom, was losing the tug of war. The very geometry of space-time was being forced to expand faster by this unseen energy. This meant that gravity, once thought to be the great conqueror, was powerless on the largest scales. Galaxies that had once been destined to slow, perhaps even fall back together, were now doomed to drift further apart forever. When scientists compared this new power to the most violent known phenomena in the universe, the scale of its dominance became clear. Supernovae, the titanic explosions of stars, were brilliant but local. Quasars, powered by the feeding frenzy of supermassive black holes, shone across millions of light years, but were still just beacons within galaxies. Even gamma-ray bursts, the brightest known flashes in the cosmos, could only momentarily outshine a single galaxy before fading into darkness. Dark energy, by contrast, worked everywhere, always. It did not explode, flare, or roar, but its influence was relentless, affecting every cubic centimeter of space, even the voids between galaxies. It was not an event, but a condition of existence itself. This realization changed cosmology overnight. The universe was no longer a great machine running down towards stillness. It was a runaway, gaining speed, carried on an invisible tide, and with this shift came a profound unease. If the universe was accelerating, what would its future look like? Would it expand forever, becoming colder and emptier with each passing eon? Or could this repulsive energy grow even stronger, tearing apart galaxies, stars, planets, even the atoms themselves, in a final catastrophic event? The thought was staggering. For the first time, astronomers were forced to confront the possibility that the ultimate fate of the cosmos might be determined not by gravity's embrace, but by something that repelled. A power that seemed to want separation, distance, isolation. This was the scientific shockwave of the late 20th century. The discovery that the universe itself was not slowing to rest, but hurrying toward an unknown destiny. It was as though reality had whispered a secret, one that we were never meant to hear, about the true balance of power in existence. And that whisper would haunt cosmology for decades to come. The shock of discovery did not end with a single graph of distant supernovae. It was only the beginning. If the universe was accelerating, proof had to be written into its very fabric. Not just in the light of a few exploding stars, but across the sky itself. Astronomers turned to the oldest light in existence, the faint, whispering glow left behind by the Big Bang. The cosmic microwave background, or CMB, was first detected in 1965. A discovery that revealed the universe's birth cry had never truly faded. It still bathes the cosmos in microwaves, a nearly perfect black-body glow just 3 degrees above absolute zero. But this light was not perfectly smooth. It was dappled with tiny temperature variations, subtle fingerprints of structure forming in the early universe. If cosmic acceleration was real, it would have left its mark here too. Enter WMAP, the Wilkinson Microwave Anisotropy Probe. Launched in 2001, it spent 9 years mapping the entire sky with exquisite precision, turning the once blurry afterglow of creation into a detailed portrait of the infant cosmos. The patterns were unmistakable. The universe was flat, just as inflation theory predicted. But the amount of matter present was far too small to explain this flatness on its own. Something else had to make up the balance. MAP's data showed that ordinary matter, the atoms of stars, planets, gas, and dust, made up less than 5% of the cosmos. Dark matter accounted for another 25%. The remaining 70% had to be something else entirely. Something smooth, something invisible, something that did not clump or cluster but instead filled all of space evenly. This was the first precise measurement of what would soon be called dark energy. The results were staggering. The universe was not just a little bit influenced by this hidden power. It was dominated by it. If the cosmos were a stage, then ordinary matter, everything humans have ever seen, was little more than the faint glow of footlights. The true stage was being stretched beneath it by a silent hand. But the CMB was only one piece of the puzzle. To be certain, astronomers needed to trace this acceleration across cosmic history to see how galaxies had been drifting apart over billions of years. They measured redshifts, the stretching of light waves as space expands. Every galaxy carries in its light a record of its motion. The farther away it is, the longer its light has been traveling, and the redder it appears. By compiling millions of these measurements, scientists could build a map not just of where galaxies are, but how they have moved through time. Patterns emerged. In the early universe, galaxies were closer together, packed into a dense web of matter. Over billions of years, this web stretched and thinned, the voids between filaments widening. And with each new survey, the expansion rate appeared to quicken, matching the story told by the supernovae and the CMB. A second method, baryon acoustic oscillations, gave yet another line of evidence. These are the frozen echoes of pressure waves that rippled through the early plasma of the universe, leaving a preferred scale, a kind of standard ruler imprinted on the distribution of galaxies. By measuring the apparent size of this feature at different cosmic epochs, astronomers could track how space itself had grown. Every measurement pointed toward the same conclusion. Acceleration was real. Even gravitational lensing, the bending of light by the gravity of massive structures, offered clues. As space expands faster, the growth of cosmic structures slows because matter has less time to collapse under its own gravity. Surveys of lensing patterns showed exactly this effect. The cosmic web was growing more sluggish, stretched apart by an invisible pressure. Piece by piece, the evidence converged. By the time the Planck satellite completed its mission in 2013, cosmologists had built the most precise model of the universe ever assembled, the LCDM model, where L represents the cosmological constant, the simplest candidate for dark energy. Its conclusion was stark. Nearly 70% of the universe is made of this mysterious energy. Dark matter, though invisible and exotic, made up about 25%. Ordinary matter, the stuff of life, was barely 5%. Humanity's picture of reality had been rewritten. The universe was not gently coasting. It was on a kind of runaway trajectory. Galaxies would continue to separate until in the unimaginably distant future, they would vanish from one another's skies entirely. The night would grow emptier, the stars of foreign galaxies lost forever to sight. This was not the quiet, symmetrical universe once imagined by Newton or even Einstein. This was a cosmos with a destination, an endless, accelerating expansion into silence. And with this revelation came a new, uneasy question. If the universe was ruled by this invisible power, what was its ultimate plan? Would the acceleration continue forever, leaving a cold, dark cosmos where only the fading embers of dying stars remained? Or could this hidden energy grow stronger with time, tearing galaxies apart, shattering stars, pulling even atoms to pieces in a final, catastrophic big rip? For now, there was no answer, only data, and the growing awareness that the more the universe was observed, the stranger it seemed. The deeper astronomers peered into space, the more it became clear that they were not just witnesses to the cosmos. They were witnesses to its transformation, catching it in the act of something vast, silent, and unstoppable. Dark energy was no longer just a subtle influence, no longer a mathematical adjustment in the margins of equations. It had revealed itself as the ruling power of the cosmos, the unseen monarch of reality. Its presence was everywhere, woven into the very geometry of space, and its reach was infinite. Unlike gravity, which grows weaker with distance, dark energy is constant, filling all of space uniformly. And as the universe grows, so too does the stage on which it acts. Every second, more space comes into existence, and with it, more of this invisible energy. This is the most unsettling truth. The larger the cosmos becomes, the more dark energy it contains. Its grip does not loosen with time. It tightens. The expansion does not slow. It accelerates. The universe is not merely expanding. It is running away. The implications are staggering. In the distant past, matter and radiation were dominant. Gravity held sway, and galaxies formed under its guiding pull. But as eons pass, matter becomes ever more diluted, and dark energy's proportion grows. Its quiet pressure will eventually drown out all other forces. If this trend continues, the fate of everything is sealed. Imagine a future where galaxies drift so far apart that their light can no longer bridge the growing gulfs between them. Billions of years from now, the night sky would be stripped of its galaxies, leaving each island of stars utterly alone in the dark. The cosmic web itself would unravel, its filaments stretched until they vanish beyond each other's horizons. And this is only the beginning. Physicists have dared to ask what would happen if dark energy is not constant, but grows stronger with time, a possibility suggested by certain theories of phantom energy. In such a universe, the acceleration would increase without limit, building toward a catastrophic crescendo. This nightmare has a name: the Big Rip. First, galaxy clusters would be torn apart as the space between them expands faster than gravity can hold them together. Then, galaxies themselves would dissolve, their stars set adrift as expansion outpaces their mutual attraction. Planets would be flung from their orbits, stars ripped away from their companions, solar systems shredded like cosmic confetti, and still the acceleration would climb. Eventually, the stars themselves would be torn apart, the atoms within them stretched until they disintegrate. In the final moments, even the very fabric of matter, protons, neutrons, electrons, would be wrenched apart by the runaway expansion. The universe would end not in fire or ice, but in a silent, absolute unweaving, a cosmos stretched to nothingness. Such a vision is not a certainty. It depends on the exact nature of dark energy, something science has yet to determine. Perhaps it is a cosmological constant, a steady pressure that will push forever but never grow. Or perhaps it is a dynamic field, its strength waxing with time until it erases everything. The equations allow both possibilities. The data, so far, cannot choose between them. This uncertainty hangs over cosmology like a question too vast to fully face. Because dark energy is not just a discovery, it is a boundary, a reminder that the universe may hold principles that lie beyond human comprehension. It is a presence that seems less like a force and more like a property of existence itself. What name can be given to something that is everywhere yet untouchable? Something that outweighs galaxies, bends destiny, and governs the future. Perhaps dark energy is not its true name, but only a placeholder, a word for our ignorance, for the shadow that falls where understanding ends. And so the investigation deepens. Every telescope, every probe, every sky survey becomes part of a single, desperate project to pierce the veil and glimpse what truly drives the universe forward. The more that is learned, the more the mystery grows. Dark energy has taken its place as the central character in the cosmic story. It is not merely a background effect, it is the plot itself, the force writing the final chapter of reality. And as the universe continues its race toward an ever-accelerating future, one haunting question remains. Is this expansion merely the prelude to eternity? Or the countdown to an end so complete that even the memory of existence will be stretched beyond reach? The discovery of dark energy left cosmology standing at the edge of a precipice. Observation had revealed the effect, the acceleration of the universe, but offered no clue as to the cause. What could possess such strength, such reach, such persistence? Scientists turned first to the idea that had haunted physics for nearly a century, Einstein's cosmological constant. In 1917, when Einstein first applied general relativity to the entire universe, he discovered something unsettling. Gravity alone would make the cosmos collapse. To counteract this, he introduced an extra term into his equations, a constant, denoted by the Greek letter L, that acted as a repulsive pressure, holding the universe in balance. But when Edwin Hubble revealed that the cosmos was not static but expanding, Einstein abandoned the term, calling it his greatest blunder. For decades, L was left behind, a mathematical curiosity collecting dust in the margins of theory. And yet, in the late 20th century, L returned, not as a blunder, but as a possible explanation for the accelerating expansion. If L is real, it means the vacuum of space itself carries energy, an intrinsic, irreducible pressure that pushes the universe apart. This would make dark energy not a substance or a field, but a property of spacetime itself. But there is a problem. Quantum field theory predicts that the vacuum energy should be staggeringly huge, 120 orders of magnitude larger than what is observed. This is not just an error, it is the largest mismatch between theory and observation in all of science. And so cosmologists began to ask, what if dark energy is not constant at all? This gave rise to the idea of quintessence, a slowly changing dynamic energy field permeating the universe. Unlike L, which is fixed, quintessence could evolve over time, waxing and waning in strength, shaping the past and future of cosmic expansion. If quintessence grows weaker, expansion might slow, perhaps even reverse, leading to a far future collapse, a big crunch. If it grows stronger, expansion could accelerate toward catastrophe. This opens the door to an even stranger scenario: phantom energy. In this model, dark energy does not merely remain constant as space expands, it grows stronger. Its pressure increases as more space is created, causing acceleration to skyrocket toward infinity. The result is the terrifying vision of the Big Rip, galaxies torn apart, stars scattered, planets flung from their orbits, atoms shredded, and eventually, the very fabric of space-time itself torn asunder. This possibility is deeply unsettling, but it cannot yet be ruled out. Others argue that perhaps dark energy is not an energy at all. Perhaps the equations of gravity themselves are incomplete. In modified gravity models, Einstein's general relativity might be only an approximation, accurate on small scales but missing a subtle correction that reveals itself on cosmic distances. In these theories, the universe accelerates not because of a mysterious energy, but because gravity behaves differently than expected over billions of light years. To rewrite gravity would be no small thing. It would shake the foundation of physics. Yet some researchers suspect that this might be necessary, and telescopes are now looking for the subtle fingerprints of modified gravity in the way galaxies cluster and light bends. And beyond even this lies the most audacious speculation of all, the multiverse. In this vision, dark energy's value is not a universal law, but a cosmic lottery ticket. The universe might be just one of countless regions, each with its own set of physical parameters. Most of these hypothetical universes would be sterile, torn apart by too much dark energy or crushed by too little. Only in a tiny fraction would conditions allow galaxies, stars, and life. Perhaps it is no coincidence that we live in one of these rare universes. Perhaps observers can only exist where dark energy has the right value to let them. But this explanation raises its own philosophical weight. It suggests that the most powerful force in the cosmos may be nothing more than an accident of existence, a byproduct of a reality far bigger than we can see. Each theory reframes the nature of power itself. If dark energy is a cosmological constant, then the most powerful thing in the universe is not a force, but a property of being. If it is quintessence or phantom energy, then cosmic destiny is not fixed but dynamic, an unfolding story with an uncertain ending. If gravity itself must be rewritten, then the universe is stranger than Einstein ever imagined, and spacetime may hold secrets that no equation yet captures. And if the multiverse is real, then even the universe itself may be just one note in an eternal symphony, a single ripple on an infinite sea. These ideas do not compete. They coexist in a strange intellectual landscape, each demanding evidence, each waiting for the verdict of future experiments. And so the quest continues. For in the search for dark energy's true nature, humanity is not just trying to explain a cosmic phenomenon. It is wrestling with the meaning of existence itself. Because to understand dark energy is to understand whether the universe is temporary or eternal, whether it ends in collapse, in a rip, or in an endless, frozen silence, and somewhere, in the data not yet gathered, in the light not yet measured, in the theories not yet written, lies the answer. An answer that could redefine the word power forever. The mystery of dark energy has become the central quest of modern cosmology. If it is the most powerful thing in the universe, then to understand it is to glimpse the deepest workings of reality. And so, humanity has begun to build its most ambitious instruments. Colossal eyes turned toward the night, designed to measure the universe with exquisite precision. On a remote mountaintop in Chile, beneath some of the darkest skies on Earth, a new observatory is waiting to awaken. The Vera C. Rubin Observatory, a facility unlike any before it, will begin its 10-year legacy survey of space and time, a project that will capture the entire visible sky every 3 nights. Its massive 8.4-meter mirror will sweep across the heavens, collecting images so deep and detailed that it will reveal billions of galaxies. Over the course of a decade, it will create the largest time-lapse of the universe ever attempted, a cosmic movie stretching across billions of light years. Through this data, astronomers will watch how galaxies drift apart, how cosmic structures evolve, and how the fingerprints of dark energy are imprinted on the geometry of space. But the Rubin Observatory is only one key in the lock. In July 2023, the Euclid mission, led by the European Space Agency, was launched into orbit. Euclid is a space telescope dedicated entirely to mapping the dark universe. Over 6 years, it will survey 15,000 square degrees of sky, nearly a third of the entire celestial sphere, measuring the shapes and positions of galaxies with extraordinary precision. By tracing gravitational lensing, the subtle bending of light as it passes through cosmic structures, Euclid will chart how dark energy has shaped the expansion of the cosmos over time. And waiting just over the horizon is NASA's Nancy Grace Roman Space Telescope, the spiritual successor to Hubble, with a field of view 100 times larger. Roman will measure the distances and redshifts of thousands of supernovae, map the distribution of galaxies, and tighten the constraints on dark energy strength like never before. Together, Rubin, Euclid, and Roman form a three-pronged attack: ground-based surveys, space-based maps, and precision supernova measurements, all converging on a single question: what is driving the universe apart? On the deserts of Arizona, another instrument is already at work. The Dark Energy Spectroscopic Instrument, or DESI, is measuring the light from 40 million galaxies and quasars. Its robotic fiber optic system can target 5,000 galaxies at once, capturing their spectra in a single exposure. From these spectra, astronomers extract redshifts, the stretching of light caused by cosmic expansion, building a three-dimensional map of the universe more detailed than anything ever made. This map will reveal the cosmic web on the largest scales, showing how galaxies are arranged like beads on filaments, separated by great voids. From this structure, physicists can trace the subtle tug-of-war between gravity and dark energy across cosmic history. Each of these instruments is like a key, slowly turning in the lock of the universe. Each observation is a new tooth aligning with the truth. But even with all this power, the answer will not come easily. Dark energy hides in the faintest signals, in the slight statistical differences between billions of galaxies, in the tiniest distortions of light, in the slow drift of cosmic time, and so, data must be gathered patiently over years, sometimes decades. The surveys will fill petabytes of memory with the light of distant galaxies, which teams of scientists will analyze, searching for patterns, correlations, whispers of the underlying law. In a way, these projects are less like experiments and more like pilgrimages. They are long journeys into the deep night, seeking a glimpse of something beyond imagination. And with each observation, the models grow sharper. The parameters that describe dark energy's strength are narrowed. The possible futures of the universe are constrained one by one. But the final answer is not yet known. Whether dark energy is constant, dynamic, or something stranger still, remains hidden. This is the quiet drama of modern science. A patient struggle against the darkness, waged not with swords or fire, but with mirrors, detectors, and mathematics. For if dark energy is truly the most powerful thing in the universe, then these instruments are humanity's attempt to speak to it, to ask it what it is, where it comes from, and what fate it holds in store. And somewhere in the next decade of data, in the images not yet taken, in the light not yet measured, the universe may finally whisper back. In the end, the most powerful thing in the universe is not a weapon forged in the hearts of stars, nor the crushing weight of a black hole's event horizon. It is not violent, not explosive, not even visible. It is silence itself, the quiet expansion of space, the invisible pressure that gives the universe room to breathe. This power does not shout. It does not announce itself with fire or fury. It simply stretches everything, slowly, relentlessly, carrying galaxies apart as though guiding them toward their own destinies. Perhaps this is the most humbling truth of all, that ultimate power is not measured in destruction, but in creation. Dark energy is not tearing the cosmos down. It is making space for it to exist, expanding the stage upon which every galaxy plays out its story. And somehow, on a tiny rock orbiting a small star, one species of fragile primates has noticed. They have measured the redshifts of galaxies, traced the afterglow of the Big Bang, mapped the geometry of space, and discovered that the universe is running away from them, faster and faster with every passing moment. In that act of noticing, they have done something extraordinary. They have turned the universe into something that can wonder about itself. The most powerful thing in the cosmos may not even be dark energy. It may be the fact that consciousness arose in a universe destined to drift apart. A spark of understanding, in the brief moment when galaxies were still close enough to see one another. But what comes next is a story no human will witness. Billions of years from now, the cosmic web will fray. Galaxies will recede beyond each other's horizons, their light unable to cross the ever-growing chasm. The night sky will empty. Future civilizations, if they exist, may never know that there were once countless galaxies scattered across the heavens. For them, the universe will appear cold, lonely, and still, its great expansion hidden by the very distance it has created. And yet, there is a strange beauty in this destiny. A universe set free is a universe that was never meant to stay bound. Perhaps this is the most elegant truth. That reality is not a prison of gravity, but a vast, unfolding freedom. As the last light of the last galaxy drifts into the distance, the universe will not die screaming. It will grow quieter, softer, until everything is stretched beyond reach, a final, infinite exhale. And so one question remains, the question that no equation can answer, no telescope can measure. Do we fear this ultimate power, this invisible hand that is guiding us toward an unknown future? Or are we witnessing the most graceful truth about existence, that the universe was always meant to fly free? The camera fades into darkness, the stars thin, then vanish. Only the deep black remains, and in that darkness, the faintest whisper. The story of the universe is still being written,